Okay, so I already discussed this. Now for hyperbolic equations, we can also use the same finite difference scheme. I'm going to give you an example of a hyperbolic equation. So this time partial square u partial t square equal to partial square u partial x square. Has anyone seen this equation before? Yes? What is that equation? The wave equation, exactly. So this equation describes the propagation of waves in a one-dimensional domain. All right. For example, you can easily plug in u of x and t equal to any function f of x minus t, or any other function of x plus t. If you plug this into the differential equation, you're going to find out they are both solutions of this differential equation. So what does this mean? This means f of x minus t means if you have a particular waveform at time equal to 0, at time equal to 1, the same waveform gets shifted in space by 1. And from the plus and minus sign, you can see the same waveform can be shifted both in the positive direction and in the negative direction. So this equation describes waves that goes in both directions, that can go in both directions, and also superpositions of these waves going into both directions. This is a hyperbolic equation now, because if you have a perturbation at a particular point in time and space, that perturbation travels at finite speed. It travels only at positive and minus 1 speed. It doesn't affect anything that is beyond this cone of influence. So x and t, if you put a perturbation here, the perturbation propagates along these two lines and only influence solution within this infinite triangle. Or if you have multiple spatial dimensions, it's a cone that becomes wider and wider as time evolves. So that's why it is a hyperbolic equation. Okay, if you learn ODEs, you probably have already learned how to convert a differential equation that has higher order derivative in time into differential equations that only has first order derivative in time. Right? How many people have seen something like that, converting a high order ODE into low order ODEs? Oh, only a few. Okay. It's a very simple trick. Once you see it, it's obvious. Okay, so I'm going to use this PDE as an example, but it's the same idea as ODE. So conversion to first order derivative in time. I'm going to define another variable, v, defined as partial u, partial t. Okay, so now I'm going to look at what is partial u, partial t, and partial v, partial t. I'm going to look at this system of differential equations that describes this evolution of two fields simultaneously. And I want to express them as functions of u and v. Now, what is partial u, partial t expressed in u and v? What is the simplest way of expressing partial u, partial t in terms of u and v? It's just v, exactly, because I defined v to be partial u, partial t. Now, what is the simplest way of expressing partial v, partial t as a function of u and v? Yes, because partial v, partial t is the second order derivative of u with respect to t. So that's, if you just plug in the definition, it's actually second order derivative in time, which according to the original partial differential equation is just a partial square u partial x. All right. So another way to write it is partial t of u and v is equal to the collection of v and partial square u partial x square. And I can solve. I can approximate this in terms of ordinary differential equations using the same finite difference we discussed before. So the approximation in U is, let me actually erase this to have more space. So the approximation of U is dui dt equal to what? Vi, right? And the approximation of dvi dt is, I've written this many times now, ui plus 1 minus 2ui plus ui minus 1 divided by delta x squared. And this time, when we use ODE45 or use any ODE integrator, we are evolving a vector that is twice as long as the number of grid points we need to solve. It's twice as long because each grid point has a variable v and has a variable u. But this is still a set of ODEs. It's just twice as big. All right? So we can solve hyperbolic differential equations that way. Basically, we learned how to approximate a differential operator in space. And that approximation can be used in all kinds of differential equations. It's very powerful. Any questions on this? Yes? This is just one of them. Good question. Yeah. Some of the hyperbolic equations are already in this form. So some of the hyperbolic equations, they are already in first order derivative in time. And so you're going to see from the look of the hyperbolic equation, there can be several different forms of the hyperbolic equation. The common theme or the commonality between these differential equations is really the domain of influence. So as soon as you have a domain of influence that looks like a cone, where the propagation of information is at finite speed instead of infinite speed, you know you have a hyperbolic equation. All right, any other questions?